So after we've seen how links get adapted in wireless mesh networks and how they are judged and how paths are judged, then let's have a deeper look on how this information is actually used to decide on the actual routing, so the layer 3 part. So first of all, we have to differentiate between two basic concepts. You may know that from different lectures, link state or distance vector routing. So both were invented in the late 50s, so they're quite dated already, but still used everywhere. So a very popular algorithm for link state routing is the Dijkstra algorithm, which uses a relaxation by visiting the closest nodes first and then calculating the optimal paths to them. So this is a classic example where a source node solves the shortest path problem. So it uses the edge weights, the link characteristics in our case, to find the shortest path to different destinations. In other words, it would choose who would forward the message there. So for this, complete network information is necessary at any given source, any source of a stream. For that, the link information needs to be exchanged before on the network. This ensures that the algorithm converges fast to finding the optimal path, but only if the information, the link information, is correct that it received. So if you imagine a bigger network where the links are also changing over time, for example, wireless links, especially if the nodes are moving, then by the time the information may have arrived at the source node, it might be outdated. So even if the algorithm itself might converge fast, the information that is given, the input parameters, might be wrong. However, for wired links, this is much more applicable, as this algorithm is used in today's internet in the algorithms ISIS, so intermediate to intermediate system, and open shortest path first. So the other type, distance vector routing, follows a distributed form. So a well-known example for this is the distributed Bellman-Ford algorithm. I'm going to show you a very simple example. The cost to all known sink or destination nodes is exchanged here in distance vector routing. So for example, if we have node K here, it's exchanging its own information to all its neighboring nodes. We use the hop count here as a distance metric just for simplicity, because I don't want to go with the decimal numbers here. We can also assume lossless links. So it will show that the destination, the distance to itself is 0, the distance to D, to I, and to S is 1 in hop count. So when node S receives this information from K, it adds its own distance towards K on this information, and then it incorporates also its own neighborhood and the previous knowledge about from other nodes. So we can see that, okay, for S, the distance to itself is obviously also 0. The distance to K is 1, not 0, because there's a link in between. And the distance to D, which is 1 for K, is 2 for S, because 1 is added. For I, it's 1 because it's direct connection, and this is what S knows from its own neighborhood information. The difference here is that the links do not, the nodes are not communicating about links which are far away. That's different than in link state routing. So these types of algorithms have a slower convergence to optimality in calculating and in when the information is exchanged, but also they depend less on the full graph knowledge. So also a characteristic of these classes of algorithms is that if a new link arrives, the information is the good news travel fast, so the other nodes know it very, very soon. But if a link goes away or fades away, the information about this will not arrive very soon and may lead to the count to infinity problem. If you want, there's good explanations about this online, you can look this up. So these types of algorithms were used in the early ARPANET, so the predecessor of the internet. This is also how it is done in Batman, because of the volatility of wireless links. So now we know how the routing information is calculated and also spread in the network, and we know it is done using the link statistics and metrics from the first section of this chapter. The remaining question now is when it is done. So there are two different types for this, on-demand and proactive protocols. In on-demand routing, a very famous example for this is AODV, ad hoc on-demand distance vector routing. The calculation of new routes is triggered when information is present, so it's on-demand routing. And the network is flooded with route requests, and then a route reply is formulated through the shortest path back to the originator of the flood. This is different in proactive routing. All routes get calculated to any node, even if some of them are never used. This might sound very much, especially for bigger networks, but the good thing is that very often routing only depends on either source or destination. So it's not specific to any source or destination combination, but only specific to the destination. So if we compare those two ways to when to create a route, we see that on-demand routing is more scalable and incurs less overhead, but the initial latency, so the time that is spent while creating the routes, is much higher than in proactive routing. So be aware that this is a very general comparison on the possibilities of those methods. So one can still implement a scalable and low overhead proactive protocol compared to some inefficient on-demand protocol. But generally it's easier to design a proactive protocol with low initial latency because of the way those are structured. The next step in the routing process is forwarder selection. So after the routing information is calculated through either link state or a distance vector mechanism, the question is how is this information applied so the routing can actually take place. In other words, the question who decides on the path. So at first there's something called source routing, where the source decides on the full path. Effectively this means that the source would send a list of hops with the message header. So each of the nodes on the path would just take out its own node name and send it further to the next hop in the list. So obviously this is only possible if a link state routing algorithm has been applied before, because otherwise the source would just not know where to send it to after the first node. This has the advantage that it requires less intelligent relays or less active relays also. Another method is where each of the nodes on the path would decide its next hop towards the source. So there would be only the destination, the message header as the goal to go to, and each of the nodes on the path then would decide. So S would decide that it would forward to K, but would not tell K where to forward it to then. Well, in this example, it's quite obvious because they're directly connected here, and they may have a good connection. But K would decide on its own where to send it to. So this works with both link state and distance vector routing calculation. But each of the nodes on the path would have to perform its full link state calculation here, so S and K. So it's a bit more intensive in calculation. As Batman is using the distance vector routing algorithm, it cannot use source routing at all, so it uses a distributed form of routing. So now the question who decides on the path is answered. So a question remaining is how many these forwarders should forward. So the classical approach in communication networks is, you may have heard that in other lectures from our chair, store and forward. So what is received by a node is sent out again, if the node is a forwarder. So this would correspond to a forwarding rate of 1.0. In mesh networks, however, it can make a lot of sense to use other forwarding rates than 1.0. So they can be smaller or bigger than 1. Smaller, especially useful for multipath. We come to this in the next lecture. But they can also be greater, for especially if there's link loss, and the mesh protocol decides to cover up for this. So in this example, we have here a forwarding rate of we have a link loss of 50%. So the ETX, the expected transmissions, would be 2 for this link. So node I has decided for a forwarding rate of 2. The node uses a credit counter, which is incremented by the forwarding rate for each packet it receives. So I have a small event table here where we see that if a packet is received, the credit counter is incremented by the forwarding rate, so it's 2 now. And as a consequence, the node transmits 2 packets, decrementing the credit counter by the number of packets it has transmitted. So these forwarding rates can also be decimal. So here we have an example for forwarding rate of 1.5. So for receiving 1 packet, increment by 1.5, transmitting 1, decrementing by 1 because it is send out 1 packet. And after receiving another packet, it sends out 2 because the credit counter was 2 then, and a 0 afterwards. So finally, recoding and feedback, or the question, what should I forward? I've talked about the classical approach just now, store and forward, this is also relevant for feedback, because if you see here an example where a node has to transmit 2 packets, one is red and one is blue, and there's a channel that erases one of the packets randomly. So I cannot know which of the packets have been erased, meaning there's the feedback mechanism going on here. So J sends back, I haven't received the red one. So I send the red one again, and they both have all the packets. This is a classical approach of ARQ, automatic repeat request. This is, by the way, also done in Batman's link layer feedback mechanism built in the Wi-Fi driver. But let's go from the global perspective to a local eyes node. So let's go from the global perspective to node I's local perspective. From previous experience, I knows that its link to J has a packet error rate of 50%. So it could send 50% of redundancy to overcome the loss. But which packet should it repeat now, the red or the blue one? It can't know that because the loss is random. So network coding gives the answer to this question. Because if I can't know which packet to forward, it can just combine both packets. If you mix red and blue, we all know that this is purple. So if any of the packets gets lost, the red or the blue one, then J has maybe at least one and the violet one, and it can subtract one from the other. So this is a very simple way to describe how network coding works. And surprisingly, what works with colors also works with packets and numbers. But more detailed information you'll get in the network coding lecture, which I can recommend on this place. The property of always sending innovative information is especially interesting for mesh networks, as they can also do it at intermediate nodes, because RNC enables recoding, so that relay nodes, intermediate nodes, can recombine packets they have received and then always send something new to their next hop. This is especially interesting for complex multipath topologies, which I will discuss in more detail in the next lecture. Also, no signaling is necessary for which packet a node should forward, so because they can always create new color shades by varying how they combine their input packets. Also, decimal forwarding rates make more sense here because instead of having to choose which one of the packets to forward, say for a forwarding rate of 1.5, the third packet a node should forward, it could just send a combination of the previously received. Also, the feedback, so what destination sends back to the source can be sparser, because a destination can decode the packets if it has as many independent color shades as there were input packets. This is called generation size in network coding. This means that the destination can signal back, I am missing 3 packets, for example, from this generation, but it does not have to feedback the exact packet numbers it misses. So now we'll come to another of these demos where I show you how the routing and feedback mechanisms I just explained are used in Batman.